This video is about the SUFARLDCSV program. That program is intended to produce a smooth floating datum from shot and receiver statics. One of my previous videos describes the CSV input queue files needed for the SUFARLDCSV program. Another of my previous videos explains the purpose of a floating datum. This video explains the algorithms and parameters that SUFARLDCSV uses to produce the smooth floating datum. You will notice that I discuss many details about the functioning of the SUFARLDCSV program. I review these details because the main algorithm is something I developed based on knowledge gained from many 2D and 3D seismic surveys. So, I believe this video is the only place you can find an explanation of the main algorithm, although similar algorithms probably exist in other programs. This video assumes you know what a floating datum is. In preparation for this video, you might want to watch my video Floating Datum, What, Why, How, and my video Floating Datum and Statics Issues. Extensive examples and tests for the program discussed here exist in the demos directory. First, a quick overview. Example setups for SUFARLDCSV follow. For 2D and for 3D, the SYN and RIN files are queue files containing shot statics and receiver statics. They can be produced from SPS2 files or other methods via SUToolCSV, spreadsheets, and other means. See my multiple videos about all that. Note that for 2D, the CDP locations are input via another queue file in SYN, while for 3D, the CDP locations are defined using an input grid in R file. The output is another queue file containing the smooth floating datum. The SUFARLDCSV program contains two types of algorithms for smoothing. One, the approximate robust local algorithm, ARL for short. I just made up that name, mostly to make it clear that the SUFARLDCSV program also contains other types of smoothing. Two other algorithms which are based on simple averaging of values over a specified number of CDPs. To understand the ARL algorithm in SUFARLDCSV, assume that a large amount of static values are input at these locations. And assume we want to get a smooth static value at CDP location X. Then, for CDP X, the ARL algorithm returns the average static of all points in this circle. But if CDP X is near the edge of coverage, the ARL algorithm returns the estimated average static that would exist if the static trend near the edge continued outward. And if CDP X is far outside the edge of coverage, the ARL algorithm increases the size of the circle and then returns the estimated average static that would exist if the static trend near the edge continued outward. After the ARL algorithm produces estimated average statics at all CDPs, several other simpler algorithms reduce any short spatial period jitters along the CDPs. The first of these simpler algorithms just averages the ARL statics over any number of CDPs that you specify. The second of these simpler algorithms uses a similar averaging, but employs a technique which leaves its output static values more centered. For 3Ds, these simpler algorithms are also run in the cross-line direction. Any or all algorithms can be turned off by parameters. If all algorithms are off, the output static at a CDP is from the nearest input point. Next, I discuss how the algorithms in SUFARLDCSV produce a smooth floating datum from shot statics and receiver statics. First, for typical 3D and 2D surveys, What is a major issue that SUFARLDCSV needs to deal with? Answer, edge effects. For floating datum, the smoothing needed is about 1 spread diameter for 3D surveys, usually referred to as 1 spread length for 2D surveys, or about twice the nominal maximum shot receiver offset distance. Now, a simple smoothing technique is to just average the values in an area, but that causes edge effects near the edges of 3D surveys and near the edges of 2D surveys. To understand edge effects, consider the last receivers of a straight 2D survey. Suppose the statics happen to have a linear trend. Now, define this simple 7 CDP averaging smoother. Apply the simple 7 CDP averaging smoother. You get this. Why? Well, here there are 3 DPs to the left that have smaller statics and 3 CDPs to the right that have larger statics. So simple averaging just reproduces the original values. But here there are 3 CDPs to the left that have smaller statics and 0 CDPs to the right. So simple averaging results in a smaller value than the original value. This also occurs on the other end of the 2D survey, of course. This still does not seem like a big problem. But remember, the smoothing needed for floating datum is about 1 spread length, which is often several hundred CDPs or more. So this edge effect reaches a considerable distance inside 2D survey lines. Now, for usual 2D surveys, there may be simple ways to deal with this. But 3D surveys have a lot more edge to deal with. Here are the shot locations of a small 3D survey, fake. 3D surveys also often have ragged edges. A small example of a ragged edge is here. Here are the receivers of that small 3D survey. 3D surveys also often have ragged edges. A small example of a ragged edge is here. Here are both the shot and receiver locations of that small 3D survey. Here are the shot, receiver, and CDP center locations of that small 3D survey. Note, the 3D grid for this survey is deliberately bad. It is slightly rotated from the best alignment and is also not centered well over the shots and receivers. This allows better tests of SUFARLDCSV, some of which are in the demos directory. Remember, the floating datum smoothing length should be about the size of the shot spread? Well, for this 3D survey, each shot spread extends over most of the survey. Even for larger 3D surveys, the smoothing distance will extend quite far inwards. Smoothing by taking a simple average of points within a circle would cause considerable edge effects. Just to be clear here, edge effects are not caused by the 3D grid boundaries. The edge that causes the effects is the edge of the area covered by the shots and receivers. Approximately this edge. The edge effects can extend large distances inward, like these arrows. Okay, that should be enough about the edge effects problem. So how does the ARL algorithm in SUFARLDCSV perform edge compensation? Well, that is what the next images explain. Note, ARL stands for the Approximate Robust Local Algorithm. I just made up that name, mostly just to make it clear that the SUFARLDCSV program also contains other types of smoothing. To see how SUFARLDCSV is reducing the edge effects, consider a collection of random points. Let us say this x is where we want to get one of the smoothed output values. First, compute the distance between x and the nearest point. Then draw a circle around x of radius nearest distance plus avrad. Avrad is a parameter value you set, typically 1 spread length. Next, average all locations coordinates of the points within the circle. This value is often called the centroid and I denote it here with a C. Now, if C is close to X, SUFARLDCSV simply averages the static values of all the points in that circle, and that is the smooth value. You set a parameter to decide how far the centroid should be to activate edge compensation. To make edge compensation easier to understand, now consider an X which is near the edge of coverage. The average location of points within the circle produce a centroid C which is far from the X location. So SUFARLDCSV performs edge compensation at this X. Looking at a close-up, first a line is made from location X to centroid C. Then a right angle line is made at centroid C. Then all locations on one side of the right angle line are averaged. This is the left centroid LC. The statics of all these LC points are averaged, and all locations on the other side of right angle line are averaged. This is the right centroid RC. The statics of all these RC points are averaged. Note that left centroid and right centroid are just arbitrary names used herein. You could also think of them as far centroid and near centroid. Now, making a line through LC and RC allows SUFARLDCSV to produce a value at X by projecting the location of X onto that line and linearly extrapolating using the average static of LC and the average static of RC. Expanding on that previous image a bit more, the average statics at LC and the average statics at RC are linearly extrapolated for X using the distance from LC to RC and the distance from RC to P. When points are well distributed throughout the circle, you can get situations where the X is between LC and RC. But this causes no problem since the projected P just results in linear interpolation rather than extrapolation. So, if edge compensation gets activated in the areas of coverage of shots or receivers, it usually makes little difference other than using more CPU time. Now, consider an X which is far from edge of coverage. Remember I said that the distance to nearest point is added to average parameter to form circle? This is why. Adding the distance to nearest point to avrad means the circle expands to include more points. The result is that X locations far outside the edges usually still have enough points to compute a centroid C and perform the rest of the edge compensation computations. As mentioned previously, edge compensation may also get activated within the area of coverage. The SUFARLDCSV program only cares how far away the centroid C is from the X. So here, points on the right side would still be used as part of right centroid group. This means that SUFARLDCSV can still produce smooth values across areas with missing shots and/or missing receivers. This image indicates how the RL algorithm deals with a 2D survey, actually just the same as for a 3D survey. For X, the nearest point is found. Then the circle is created by adding avrad to nearest distance. Then the centroid C is computed, and so on. The fact that points are on a straight or crooked 2D line does not require alteration of any RL computations. That concludes the explanation of the RL algorithm. But the RL algorithm does not produce completely smooth values. Its primary purpose is to reduce edge effects while deriving a robust approximation of the average of local values. The values derived by RL often have short spatial period jitters along the CDPs. Therefore, some further smoothing is applied to the derived RL values. This further smoothing is done by the two simple averaging algorithms that I mentioned previously. Details of these simple averaging algorithms will be presented later. Next, I show some results using the fake 3D survey. This fake survey has a static trend. You can also think of this as an elevation trend. And it also has some shots and some receivers with considerably different statics than their near neighbors. Here is a contour plot of the shot static nearest each CDP within the 3D grid. No smoothing at all. Remember, the area of shot coverage is actually within this black rectangle. Some shots have large static differences relative to their neighbors, so the effects of smoothing will be obvious. Here is a contour plot of the receiver static nearest each CDP within the 3D grid. No smoothing at all. Remember, the area of receiver coverage is actually within this black rectangle. Some receivers have large static differences relative to their neighbors, so the effects of smoothing will be obvious. Here is a contour plot of the combined shot static plus receiver static divided by 2 nearest each CDP within the 3D grid. No smoothing at all. Remember, the area of coverage is actually within this black rectangle. Here is a contour plot of the smooth shot static at each CDP within the 3D grid. After smoothing using default parameter values in SUFARLDCSV. Here is a contour plot of the smooth receiver static at each CDP within 3D grid, after smoothing using default parameter values in SUFARLDCSV. Here is a contour plot of the combined smooth shot static plus smooth receiver static divided by 2 of each CDP within the 3D grid. To be clear here, the shot statics are smoothed independently and the receiver statics are smoothed independently. For each CDP, those smooth values are just summed and divided by 2. Typically, that is the value you want to use as the floating datum, but all 3 of those values are output by SUFARLDCSV. Remember that this is the area of coverage for shots and receivers. Note, SUFARLDCSV produced good values in the area of coverage and even outside the area of coverage. Note the ragged edge is in this area and still has good output values. Now, at the risk of confusing you, here is another plot of the smooth shot static plus smooth receiver static divided by 2 of each CDP within the 3D grid. But this plot uses the CDP number as the horizontal axis. Remember that 3D CDP numbers wrap around from the end of one inline to the beginning of the next inline. Just note the smoothness here for later comparison. And here is another plot of the smooth shot static plus smooth receiver static divided by 2 of each CDP within the 3D grid. But this plot uses the transposed CDP number as the horizontal axis. Remember that 3D transposed CDP numbers wrap around from the end of one cross line to the beginning of the next cross line. Just note the smoothness here for later comparison. Here is a contour plot of the smooth shot static at each CDP within the 3D grid, but only RL smoothing has been done. Here is a contour plot of the smooth receiver static at each CDP within the 3D grid, but only RL smoothing has been done. Here is a contour plot of the smooth shot static plus smooth receiver static divided by 2 of each CDP within the 3D grid, but only RL smoothing has been done. Here is that plot using the CDP number as the horizontal axis of the combined smooth shot static plus smooth receiver static divided by 2 of each CDP within the 3D grid. Note the short spatial period jitters. Here is that plot using the transposed CDP number as the horizontal axis of the smooth shot static plus smooth receiver static divided by 2 of each CDP within the 3D grid. Note the short spatial period jitters. Here is a contour plot of the smooth shot static of each CDP within the 3D grid. But only simple averaging and smoothing has been done, not RL smoothing. You can see some edge effects. Here is a contour plot of the smooth receiver static at each CDP within the 3D grid. But only simple averaging and smoothing has been done, not RL smoothing. You can see some edge effects. Here is a contour plot of the smooth shot static plus smooth receiver static divided by 2 of each CDP within the 3D grid. But only simple averaging and smoothing has been done, not RL smoothing. You can see some edge effects. Here is that plot using the CDP number as the horizontal axis of the smooth shot static plus smooth receiver static divided by 2 of each CDP within the 3D grid. Note the edge effects. Here is that plot using the transposed CDP number as the horizontal axis of the smooth shot static plus smooth receiver static divided by 2 of each CDP within the 3D grid. Note the edge effects. Okay, now I present a fake 2D survey. Here is a plot of the shot statics and receiver statics using station as horizontal axis. The shot statics are slightly different than the receiver statics. This often occurs, especially when shots are down a hole. Note, from this plot, you cannot tell if this 2D is straight or crooked. Here is a plot of the smooth statics at all CDPs using all defaults in SUFARLDCSV. The red line is the smooth shot static, blue line is the smooth receiver static, the green line is the smooth shot static plus smooth receiver static divided by 2. Naturally, you may want to adjust parameters of SUFARLDCSV. Here, the avrad parameter has been reset to 200. Its default is 1000. Only the avrad parameter was changed. Avrad is the main RL parameter. You can also get a similar effect by turning off RL. Set avrad to -1 and increasing the simple averaging parameter navrage from its default of 10 to 40. But the ends of the line now have edge effects. Here is a plot of shot statics and receiver statics using station as horizontal axis. But in this case, many shots are missing at various locations within the line, and some receivers are missing at the ends of the line. Note in particular that there are many missing shots here, which just happens to be where the statics trend also has a large change. For extensive amounts of missing shots and receivers, set the parameters carefully. For this case, here an avrad value of 200 is tested. Remember, the green line is typically used as the floating datum value, so this may be a good enough result. Now here, the avrad parameter is still 200, and navrage parameter has been set to 20. This may be a better floating datum. A few comments about other parameters follow. Here is the setup that set avrad parameter 200 and navrage parameter to 20 and produced the smooth floating datum values in the previous plot. The SIN parameter is an input Q file with shot statics and locations, typically XYs. The RIN parameter is an input Q file with receiver statics and locations, typically XYs. The SIN parameter is an input Q file of 2D CDP locations, typically XYs. The DOUT parameter is the output Q file with CDPs, locations, smooth shot statics, smooth receiver statics, and smooth shot static plus smooth receiver static divided by 2. See my video, Floating Datum and Statics Issues, for more about these files. The avrad parameter has two related parameters as shown below. The nedge parameter sets the minimum number of points within the circle for edge compensation to be activated at that location. Nedge defaults to 2. The sedge parameter sets how far away from an output location the centroid has to be for edge compensation to be activated at that output location. The sedge parameter defaults to 10% of radrad parameter. For context, note that a half-circle disk has a centroid at 4r divided by 3 pi, or about 42% of the average value. Simple averaging and smoothing has 3 parameters specified in number of CDPs. For 3D surveys, these can be specified in number of CDPs inline and also cross-line. Now, average parameter defaults to 10. The n-smooth parameter defaults to whatever average is. The n-back parameter defaults to 3. For 3D surveys, the cross-line value defaults to whatever the inline value is. The average averaging uses the statics after the RL algorithm. The n-smooth smoothing uses the statics after the average averaging. Both average averaging and n-smooth smoothing are done after the n-back parameter has extrapolated extra CDPs outside the ends of the survey. To understand the n-back parameter, consider the end of CDPs in a 2D survey. If a trend exists in the statics, then after the RL algorithm, they could look like this. An n-back value of 3 uses the static at the last CDP and the static at the last minus 3 CDP to linearly extrapolate extra values beyond the end. And it uses the static at the first CDP and first plus 3 CDP to linearly extrapolate extra values beyond the beginning. It extrapolates the same amount as navrad and n-smooth are set to. If navrad is 10, it adds 10 extra. If n-smooth is 14, it adds 14 extra, and so on. These extrapolated CDPs are only used by navrad and n-smooth. These extrapolated CDPs are not output. For 2D surveys, they are created beyond both ends of the line. For 3D surveys, they are created beyond both ends of each inline and also created beyond both ends of each crossline. Note these CDPs are created outside the 3D grid boundaries, not the area of shot and receiver coverage. In some situations, you may want to set n-back to a larger value. An n-back value of 5 would use the static at the last CDP and the static at the last minus 5 CDP to linearly extrapolate extra CDP values beyond the last. And it would use the static at the first CDP and the first plus 5 CDP to linearly extrapolate extra CDP values beyond the first. So, after extra CDPs are created by n-back, the average parameter simply averages the statics over a symmetric number of CDPs. For the average default of 10, the statics of 21 CDPs are averaged. The center CDP static plus the next lower 10 CDP statics plus the next 10 higher CDP statics. And after extra CDPs are created by n-back, the n-smooth parameter uses a slightly more complicated technique. Taking the n-smooth default of 10 as an example, first, 21 CDPs are averaged for each CDP, exactly as done for an average. Then, the difference between that average at each CDP and the original value at each CDP is added to the original value to get an intermediate value at each CDP. Intermediate value equals original plus original minus averaged. And then those intermediate values are themselves averaged over 21 CDPs. Values smoothed by this n-smooth technique are more centered than those by the average technique. The following images make this clearer. Here is a straight 2D line with some statics values plotted. A closer view. Black are the original unsmoothed values. Red are smoothed use only average equals 100. Green are smoothed use only and smooth equals 100. Note that the green line stays closer to the original line than the red line.
That is what I meant when I said values smoothed by the n-smooth technique are more centered than values smoothed by the average technique. For the usual case where RL is doing most of the smoothing and both average and smooth are relatively small, this does not matter much. But if average or n-smooth are relatively large, you should consider this difference. Now I'm going to bring your attention to some setups you might want to use. Here, no shot statics are input, and the receiver statics and CDP numbers exist in the same file, and that file is specified as input to RIN and SYN. You might find this useful for ocean bottom cable or nodes, although in that case, you are more likely to be inputting a 3D grid in R file. Or you can also set the RIN equals none if you have no receiver statics. Here you can see that the names of location values can be altered. For 2D surveys, you usually specify two location names, XYs. But you can also specify just one name, such as shot station and receiver station. For that case, you should also specify AVRAD and CEdge in station numbers. Finally, a theoretical consideration. Consider a 2D seismic survey acquired along this surface. Suppose the receivers are evenly spaced, but the shots are distributed as shown. How should the floating datum be affected between points A and B? Well, in my opinion, since the shots at point A are contributing 3 times as many traces to the CDPs between A and B, then the shot statics from point A should contribute 3 times the weight when computing the smooth floating datum. That is what the RL algorithm does, approximately. Also remember the basic purpose of a floating datum. A floating datum is used to align the traces with the animal velocity hyperbolas. I believe it is superior to align the animal velocity hyperbolas as much as possible with the majority of the traces. Now, often you hear floating datum is a smooth surface, elevation or static. But just smoothing the surface would not cause point A to be weighted 3 times. So the results would not be the same as the RL algorithm. You might believe that smoothing a surface is a better way to obtain a floating datum. Fine, but there is an issue. Remember, a traditional way of getting a floating datum, the total statics for each CDP are averaged during stacking and then simply smoothed along the CDPs. That traditional method means that point A usually contributes 3 times the shot statics to the CDPs between A and B. So, smoothing a surface to obtain a floating datum means you are going against the traditional weighting to produce your smooth floating datum. Since the traditional method seems to have a good argument that aligns the animal velocity hyperbolas with more traces, you should prepare for a debate. Of course, the RL algorithm only approximates the traditional method because it effectively assumes traces are well distributed from each shot and to each receiver. And SUFARLDCSV can only approximate the traditional method if the input SYN-Q file only contains records for shots that actually exist. Typical SPS2S files do not contain records for shots that actually exist. Only stations where shots might exist. Finally, a few more points. 1. SUFARLDCSV does not know it is dealing with statics. It can be used to produce smooth elevations or any other similar values. 2. SUFARLDCSV does not know whether the input shots and receivers actually exist in your survey. If the actual shots or receivers are missing or badly distributed, and the result is a bad floating datum, you might want to add some fake shots or receivers at convenient locations in the input Q files. The floating datum from SUFARLDCSV is usually input to SUShiftCSV. Notice that the SUFARLDCSV locations typically are coordinates, but SUShiftCSV location keys might be such values as FLDR, shot field record number, and GAPS, 2D receiver station number, or other unique identifiers in the Q files. You can use coordinates as SUShiftCSV shot and receiver location keys as long as they uniquely identify each shot and each receiver. But the SUShiftCSV location key for SYN is almost always CDP, since the input trace headers do not usually contain CDP center XYs or any other unique identifiers. I include the documentation from SUFARLDCSV next, just so you can read it here conveniently. I'll remind you that documentation can change after this video, December 2023.